All right, well, good afternoon, everyone. I started off this morning by looking at the development historically of performance-based design and introducing how performance-based design is done today for tall buildings, and then you spent a whole lot of time the rest of the day hearing in detail how it's done today for tall buildings, and I'll complete us off here talking about the FEMA P58 methodology, the title of which is Next Generation Performance-Based Seismic Design Criteria, and which might be the way we design tall buildings and other buildings on a performance basis in the future. And I started off this morning, you may recall, talking about the Vision 2000 definition of what performance-based seismic design was all about. Procedures that enable, still spelled wrong, design and construction of buildings that will reliably be able to attain desired seismic performance measured in certain impacts, potential life safety impacts, number of people that might be injured or die, the potential loss of occupancy, how many days, weeks, months, or years you may be out of your building, potential repair costs, how many dollars it's likely going to take to get you back into the building. And then I talked about the present generation procedures, ASCE 41 and its clones, PEER, TBI, and the LA Tall Buildings Council guidelines, which really are based on ASCE 41. And the one thing I'd like to call your attention to now about all of that is that these procedures that we define as today's performance-based design approach don't really answer the basic questions and don't actually give you quantitative answers to how many lives might be lost, how much time might I be out of the facility, how much might it cost to repair the building. You don't really get that. You get nonlinear deformation demands, you get strength demands. We have acceptable values based on research data as to what might be an acceptable value of strain or of plastic rotation demand on an element, given that you're shooting for different damage levels. But the damage levels aren't actually predicted by the software that we're using. They're predicting structural parameters. We then have to sit and think about plastic rotation demands and strains and picture what the elements in the building might look like, given that they experience those demands. And then we have to try and project the answers to the owner's questions that they have as to what all of this means in terms of life safety, repair time, repair costs. And every engineer will likely come up with different answers, which is really no more satisfying today than it was back 30 years ago when we were trying to figure out individually what factor we should put on the Uniform Building Code requirements in order to meet some performance criteria. The other thing, as I said this morning about the present day procedures, is they sort of ignore non-structural performance. You spent, I guess, about 6 hours since I spoke with you last hearing a whole lot about performance-based design of tall buildings. I don't think you probably heard very much about performance-based design of non-structural components in tall buildings, and that's simply because such a thing doesn't exist and doesn't get done. The non-structural components are designed per the building code. And as I said earlier this morning, the non-structural components are typically where most of the losses that owners care about originate. There is another issue with the ASCE 41-like procedures, and that relates to reliability, something that engineers don't like to think about very much. If you read the commentary to FEMA 273, buried very obscurely in Chapter 2 to the commentary is a statement, a speculation, that if you properly design a building in accordance with what we now call ASCE 41, and the contractor properly constructs it in accordance with your design, those are both big ifs, but let's say both of those things happen, there's speculation that perhaps 1 out of 10 designs that you come up with may experience poorer performance than intended by the design. Now, that's really not a very comforting thought if you sit back and think about it. I've been designing structures for 40 years. I hate to think of how many hundreds of structures I've designed that have my stamp sitting on the drawings for sitting out there. If 10% of those are subject to failure, meaning not performing the way the owner expected, when they see design events, that means I may have a whole lot of litigation in my future. You young people, you might want to think about that. Think about all of the hundreds to maybe thousands of structures you're going to be designing. All right? 1 out of 10 is not particularly good if you're designing hundreds to thousands of structures over your career, unless the owner buys into this and is willing to accept it. Now, there's something very important here. When we design a building to the building code, there's usually not a discussion with the owner as to what performance is expected. The owner knows you're going to design the building to the building code. He knows the building department's going to do a plan check. It's going to get constructed in accordance with the building code because it's going to get inspected. And therefore, the building is going to perform perfectly. No event that ever occurs can ever do any damage to it. Not exactly what is intended by the building code, but this is what most owners think when they commission a new building. And so from time to time, we do have a severe event, a hurricane, a tornado, an earthquake. And because the building code doesn't intend that buildings survive such events without damage, they inevitably have damage. And when that happens, inevitably there are some owners of buildings, particularly buildings that were recently developed and constructed, that are unhappy about that performance. If you've designed the building to the building code and the owner of the building who commissioned you to do that is unhappy with the way the building performed, he may litigate against you. It happens. If you design the building to the building code, all you have to do to protect yourself, besides spending lots of money on lawyers, is to demonstrate that you've conformed to an appropriate standard of care. In the court, there's a lot of court evidence that suggests that the appropriate standard of care is not error-free work. It's not perfect compliance with the building code. It's general compliance with the building code, and no greater errors than your competitor located across the street would have been likely to have made when he or she designed the same building at the same period of time in the same city for the same client. Not a particularly high standard of care, but it's very well defined. And so there's a defense for us. The situation might be quite different when you're doing a performance-based design. Another thing about the 10%. No one really knows if that 10% is real or not. That was pure speculation. There were suggestions that there should be some reliability studies done to determine, is there really only a 10% chance that my building will do worse, or is it something significantly better than this? Remember that what you heard through the procedures today, most of the evaluations of the adequacy of elements, not all of them, but most of them, are done on mean estimates of demand. You run a suite of 7 analyses, you take the mean results from the analyses, you compare them against the acceptance criteria. Inherent in the fact that you're taking mean results is that there's something like a 50% chance that your actual demands are going to be larger than what you're using to check acceptance against. Now, hopefully our acceptance criteria, our permissible strains, our acceptable strengths have enough fat in them so that if you go somewhat over 20, 30, 40%, you could easily be that much over, your performance isn't drastically worse. But there's no guarantee of that. Next generation performance prediction. Well, as you know, CSI and other vendors of software are getting much, much better about giving us structural simulation capability. And it would be really nice if the next version of CSI Perform, you could model your building, including all of the non-structural components. You could push the button and sit back and watch what happens in each of your 7 earthquakes. We know what the performance of that building has been. It may or may not be acceptable to the owner, depending on what you agreed your performance objectives were, but we can see exactly what the damage is. Unfortunately, I don't think CSI is going to be producing this software anywhere in the near future, and so we're going to have to use a somewhat different process going forward into the future. We'll start, just as we do today, by deciding what ground motion or ground motions it is we're going to design for, and getting representation of those ground motions from a geotechnical engineer. We'll continue to build structural models that will have mathematical representations of beams, columns, braces, walls, and other elements. We'll subject those mathematical models to representations of the ground motion, and we will simulate the behavior not of the building, but of the structure to that ground motion. However, instead of doing what we do today, which is looking at the results of that structural analysis and saying, We're getting a plastic rotation demand of 3% radians at this beam column joint. We're getting a strain of 0.004 in this piece of reinforcing steel at the end of the wall. Instead of doing that, which really doesn't tell us directly what the damage is, we're going to try to take the results of that analysis and predict what the damage is. Then, once we know what the results of that is and what the damage is going to be, it will be fairly easy to predict the things that owners care about. How much time it's going to take to repair, what it will cost, how many people may be injured as a result of the damage that has occurred. Now, one thing about this process, it's impossible. We can't do it. At least we can't do it precisely. And the reason we can't do it precisely is because each of those steps that I just talked about entails many, many uncertainties. We take representations of the ground motion. Usually we're using records that have been recorded in past events on other sites. The code and the guidelines have good words in it about picking records that are representative of events of similar magnitude on similar condition soil sites, resulting from fault mechanisms that are similar to the mechanisms controlling your hazard at your site. All kinds of good qualitative language about what you should do when selecting ground motions. Almost never, probably never in my career have I ever had a record available to me recorded on the site where my building was going. Earthquake ground motions are a lot like snowflakes. When it snows, every snowflake is different. When you have an earthquake, every ground motion recording in that earthquake is different, and every earthquake produces somewhat different ground motions. So the 7 or 11 or 22 or 95 ground motions we pick to represent the seismic hazard, the fact is our building is not going to see any one of those ground motions. We don't know what our building is going to see. We try and pick ground motions that are representative and hope the ground motions we actually see will look something like that, but we don't know. We build a model of our building. We're very proud of our ability to build models of our buildings. We spend lots of time in college being trained in how to do this, then we spend lots of time in engineering practices being taught by our supervisors about how to do it properly, and our peer reviewers are looking over our shoulder and criticizing our modeling and telling us what we should do better. And we think we can really build models that predict exactly how the building is going to perform when it's subjected to the ground motion we can't actually predict. Well, we can't actually build models that represent the building very well either. All right? First of all, we don't model a whole lot of the building. We typically model the structure. Well, we don't even really model the structure. We sort of model the lateral force resisting system of the structure, and maybe those elements of the structure that we think are going to be sensitive to displacements induced by the earthquake, or maybe not. Maybe we put another model together and let it represent the gravity carrying system, see how it does when we subject it to lateral displacement. But the fact is, all that stuff we don't model has an effect on the response of the structure. So the structure that we're modeling is not actually the building. Let's pretend that's not true. Let's pretend we actually can build a model that exactly represents the building structure. The seismic system, the gravity system, the non-structural components that might have effects on the damping and the stiffness. Now we're going to simulate to this ground motion, which exactly represents what it's going to see, how the building will behave. Well, one of the things that we have to do is have an understanding of how much live load is going to be on the structure at the time that earthquake occurs. So does it occur at 3:45 in the afternoon when all of us are sitting here in this room? Or does it occur at 9 p.m. tonight when this room is vacant? It makes a whole lot of difference as to how much live load happens to be on the beams and columns supporting this particular room. It makes a whole lot of difference as to how much strain it might take to cause buckling of some of those elements. We have no way of knowing that. Let's ignore that for a moment. Let's pretend that we do know exactly how much live load is going to be in the structure. How are we going to predict how much damage occurs to structural elements? Well, we're going to look at things like strains and plastic rotations and plastic elongations, and based on available research data, and we have a lot more laboratory research data available today than we did 30 years ago. We can look at elements that have gone through similar levels of straining and say, oh, well, that's what they look like when they see that type of demand. Plastic rotation demand, 3% radians looks like this type of cracking and spalling in this type of element. Except that laboratory testing was done probably to a very specific loading protocol. Probably it was a ramped, quasi-static cyclic loading that actually looks nothing at all like the loading that an earthquake will induce on a structural element. The damage that occurs in structural elements is very load path dependent. You can get a very large plastic excursion one time in the beginning of an event, and then a bunch of little oscillations have about the same amount of energy dissipation as that protocol, but do a small fraction of the damage. And again, we don't really have test data that shows all of the different types of loading protocols. Let's ignore that. Let's pretend we really can predict the damage precisely. We know how the building has been damaged by the earthquake. Now all we have to do is predict the consequences. Well, that's easy. If we know how the building has been damaged, we know exactly how we're going to repair it. Except that I suggest you would probably come up for a different repair than he would for the same building. Then there's the contractor. We know that when we put out a set of drawings for a brand new building, telling them exactly what it is we want them to build, and we ask for bids, the bids always come back within like 2 or 3% of each other, right? Not exactly. So even if you know exactly what it is you're going to want built, there's huge uncertainty as what the actual cost of building that is going to be. So all of these things affect our ability to predict what the consequences of earthquake damage to our buildings are going to be. Because of that, we don't do in this next generation performance assessment methodology what we do today. What we do today is we go to Mr. Owner or Mrs. Owner and we say, so Mr. or Mrs. Owner, what performance do you want for your building? And assuming they care, you'll walk away with something, well, I want collapse prevention for a maximum considered earthquake, and I want life safety for a design earthquake, and I want serviceability or something like immediate occupancy for an earthquake that has a 50% chance of occurrence in 30 years. And you walk off and you say, fine, I'll produce that for you with our design. Fact is, you still don't know all of those things I talked about, and I think there's far greater than a 10% chance you'll be wrong. All right? So in the next generation performance assessment, rather than coming back and saying, Mr. or Mrs. Owner, you will not lose more than one life in this building if it sees a maximum considered earthquake. Your repair costs will not exceed $1 million. Your repair time won't exceed 6 months. We put bounds on this thing, and we represent our probable losses probabilistically in the form of a loss distribution or loss curve, like the one you show here, which shows for a hypothetical building how many thousands or millions of dollars it might cost to repair a building after a certain level of earthquake, and what the probability is, much as with ground motion, what the probability is that the repair cost will exceed different values. So that when you talk with an owner now, you'll say, we're going to design for an expected return to service of the building of 1 week. Might be as short as 3 days, might be as long as a month. To do this, we do modeling of the building, not of the structure so much, but of the building. We construct something called a building performance model. This building performance model, if you could see it on a screen, would look like a building. It would not include only the structural elements, it would include exterior cladding, ceilings, lighting fixtures, HVAC systems, plumbing systems, fire protection systems, elevators, all of the things in the building that can be damaged by ground shaking and the building's response to ground shaking. Associated with each one of those elements of the building, a wall, a ceiling, a light fixture, is something that we call a fragility specification. And the fragility specification is a representation of the different types of damage that can occur to that type of element, and the probability that you will experience that type of damage as a function of some structural response parameter that we can predict with analysis, such as story drift, floor acceleration, floor velocity. We represent this in the form of things called fragility curves, which tell you the probability of being in different damage states given that you experience a given level of demand. And associated with those also are consequence functions that indicate what the probable consequences of that damage are, together with upper and lower bounds, so that we know if a wall gets damaged in a certain way, it may take as little as a week to repair it to perhaps 2 weeks, and it may cost as little as $10,000 to repair it to perhaps $20,000. And by the way, there is downloadable from the FEMA website on the FEMA P58 page, which is the name of the project that developed this methodology, a database of these fragility functions which have all of this data for basically every component you would need to construct a building performance model for office buildings, schools, residential buildings, retail buildings, all of the common occupancies, for structural elements and for non-structural elements. Then we build an analytical model. We subject the analytical model to ground motion, and we predict best estimates of demands on each of the elements in our building that can be damaged. These demands are represented in terms of best estimate or median values of story drift, floor acceleration, and floor velocity. And in addition to having median estimates, best estimates of what the values of these things are, we also have representations of the probabilistic distribution of these things. How much smaller or larger than the median values, the floor acceleration, the story drift, might be. And it might be larger or smaller than we predicted because of all of the things I spoke about before. We don't really know what the ground motion is, our model isn't very good. All of those things play into the fact that the demand could be greater or less than what we think it is. We also assemble something called a covariance matrix, which is a little bit difficult to get your head around. Think of yourself taking a balloon and filling it with water, but don't fill it so full that it's going to break. It's still going to be kind of a squishy balloon. So you've got a balloon that's got some water in it, but it's not stretched very fat. If you take your hand and you grab the balloon around the middle and you squeeze it, the water sort of smushes out at the top and the bottom and balloons out above and below your hand. Then if you take it where it's ballooned out and squish it some more, it pops out somewhere else. Well, the fact is that earthquake demands in buildings, whether they're accelerations or story drifts or other demands that we use to predict performance, are a lot like the water in that balloon. An earthquake has a certain amount of energy in the periods of response of the building and is going to deliver a certain amount of acceleration and displacement and velocity throughout the building. And if you constrict where that can occur, you're going to force it to occur someplace else. Now, we don't actually knowledgeably constrict where these things can occur, but we do sort of, without thought, do this all the time by putting things like soft stories in our building, by putting things like torsional irregularities in our building. What these things do is they sort of force you to get more displacement in one place than you do in another place, or more acceleration in one place than in another place. And these covariance matrices, what they do is they represent, if you get a lot of motion down in the first story, how much motion are you likely to get in the top story? And if you get a lot of motion in the top story, how much acceleration are you likely to get in the middle story? And there actually are relationships between these things. Neither you nor I can predict them just by thinking what they are, but through analyses it is possible to predict how one will vary with the other for a specific building. Then we follow a Monte Carlo process, which is the fun part. We get to go to Monte Carlo, not really, spin a roulette wheel many times, hundreds to thousands of times, in order to explore all of these uncertainties. We basically will do thousands of analyses, not structural analyses, but thousands of simulations of the building's response to earthquake that we call realizations. And each realization represents one possible outcome of the building's response to a given intensity earthquake. And so in one of those realizations, we might assume that the yield strength of all of the beams and columns in the building actually is exactly equal to 125% of the specified value. And the damping in the building might really be 2.5%. And the live loading might really be 25% of the specified live loading. And the earthquake is actually occurring at 3 p.m. in the afternoon, and so there's about 2/3 of the standard building occupancy actually present in the building. And we go through and we calculate how much damage is in the building for that case, and we figure out what the consequences are for that case. That's one realization. Then we'll spin the roulette wheel again. This time, maybe the yield strength of the columns is actually equal to the specified yield strength. The yield strength of the beams is 150% of the specified yield strength. We're now at 2 a.m. There's nobody in the building, and the damping maybe is 3% now, because we don't really know what the damping is anyway. And again, we calculate all of the damage and we calculate all the consequences. And we do this thousands of times. It sounds very complex. It actually isn't that complex. We don't really do any more structural analyses than we do today. You can either do a linear static analysis, an equivalent lateral force analysis, and we can give you some estimates of how to convert those into mean or best estimates of demand, and also how to put uncertainties on those to represent how much larger or smaller than those demands you might be. And then by spinning this roulette wheel a number of times, we can generate a series of realizations of what the demands, acceleration, story, drift, velocity, and the structure might be for different ground motions. Then for each one of these realizations, we go through this little logic diagram that you see here that leads us through questioning what happens to the building in the earthquake. And in each one of those places where you see a pair of dice, we have a point where we might get one answer or another answer. And so we roll the dice to figure out what answer we can get. Fairly complex process. There is software available that does all of this for us. Currently, there's a piece of software out there called the Performance Assessment Calculation Tool. Again, it is downloadable free of charge from the FEMA website. It runs very rapidly on your computer. There's also a commercial developer of software who is putting out a commercial version of this. It will cost a little more, but eventually it'll hook right onto the end of your favorite analysis software and automate the process of doing all of this even more than it currently is. When you run the software, you get results out in a very few minutes that look like this. You get on the bottom of the screen a loss distribution that shows you probable repair costs, and on the top part of the screen a histogram that shows you where those repair costs are coming from. So let's say you've had an agreement with your owner that you're going to design the building so that the probable repair cost will not exceed 10% of the building's replacement value. You go off, you do your design, you do a packed analysis, you compute that probable repair cost for this building is 15% of the replacement cost. My design doesn't work, I have to revise the design, redo it. Well, how are you going to revise the design in order to get down to 10%? Well, that histogram on the top part of the screen there tells you where the repair costs are coming from. And you might see that 20% of the repair costs are coming from exterior cladding, 10% of the repair costs are coming from ceilings, 5% of the repair costs are coming from damage to concrete walls. Say, well, it sounds like cladding and ceilings are things that I need to worry about. What's affecting that? Well, it turns out that story drift is probably affecting that. So maybe I need to stiffen up my design so I have less story drift and I have less loss in those areas. So that's the sort of information you can get from this. You can get that for repair cost, you can get it for casualties, you can get it for business interruption or occupancy interruption time. You can even get it for the likelihood that your building will be red tagged by a post-earthquake inspector following the event. There are some significant benefits to this new approach. One of them is that it provides data that is directly useful for cost-benefit analyses and decision-making. So the Vision 2000 definition of performance-based design that will reliably meet expectations with regards to life safety protection, repair costs, occupancy interruption time. You can now get direct estimates of lives lost, repair cost, repair time, together with upper and lower bounds on that. If we do this properly and communicate properly with the decision makers, rather than saying, Mr. Owner, we have a deal, I'm going to design your building so that for 500-year ground motion, repair cost won't exceed 20% of the replacement value, your owner should now understand that probably 20%, might be as high as 30%, might be as low as 10%. inherently and explicitly recognizes the effect of non-structural components, which I'm sorry to say have most of the impact in earthquake losses, and permits engineers to conveniently explore the effects of what they can change in their design to improve a building's performance. Now, the one thing that we're desperately going to need to be able to use this to shove in front of a building department and get a permit is some consensus definitions of what the building code currently gives us in the way of performance. We sort of understand that the building code currently for a risk category 2 structure gives you collapse prevention performance for maximum considered earthquake shaking, gives you life safety performance for design earthquake shaking, gives you service level performance for 43-year shaking. We sort of understand that. What we don't understand is for the typical code conforming building, what are the probable repair costs? What is the likelihood of incurring, not protecting lives? How much time is it likely to take to repair the building? So at some point in the future, to make this practical for use instead of the procedures that you heard about today, we'll have a need to define for building owners what those performance measures are that are equivalent to the building, so that we can go to the building department, present our evidence that we are meeting those things, and we can get our building permit. With that, I'd like to thank you for your attention.